So shall we see your slides, but not in full screen mode?
Yeah, I didn't do that yet.
Okay, but you can basically. Okay, perfect. That looks good. So Huchao, you tell me when to do something, right?
Okay, yeah. Maybe we will have about 80% now. The talk start at 10. Shall we start it now or still wait for a while?
It's fine. So I can I'm flexible in time.
Yeah.
Chen, use a laser. Use a laser for your pointer.
I have laser pointer only when I point.
Okay, got it. Yeah.
I would suggest to wait 1 more minute and then get started.
Okay, I'll do that. Okay, so why don't we get started? I think, yeah, so I'm very happy that the organizers asked me in particular, Huichao, to chair the meeting today, which will be given by Shun Shen. So let me introduce Shun for a second here. So Shun got his bachelor in China, then he graduated from Ohio State in 2014. Then he went for his first postdoc to McGill University, and afterwards he moved on to be a Goldhaber Fellow at Brookhaven National Laboratory. And currently he's at Wayne State University as an assistant professor, where he started in 2018. And he's involved in major collaborations like the JetScape-Xscape project, as well as the BEST collaboration, which is more relevant for the topic he's going to be reporting on here in a sense. And he also received a couple of awards during his career already. And I think the most recent one seems to be this UPAP Young Scientist Prize for Nuclear Physics in 2019. So with that, I think we're looking forward to a nice talk about the dynamical modeling of relativistic heavy ion collision at the Beam Energy Scan energies. And yeah, you have 60 minutes, Shun, and then afterwards there's plenty of time for questions. Thank you. Yeah, go ahead.
Okay, yeah, thanks for the introduction, and also thank the organizer for inviting me here to give the talk. So I will basically give you a summary or overview about the recent progress on trying to achieve a dynamical description of heavy ion collision at the various of collision energies. So, so let me start. Wait, sorry. Yeah. So okay. So yeah. So let me start with a brief, general picture of heavy ion collisions. So at the initial stage, we have two nuclei collide with each other with relative speed. After a few small amount of time, the system will evolve from far from equilibrium to near somewhat equilibrium, where when you can apply hydrodynamic description to the microscopic dynamics of the systems. As the system expands and cools, the system will go through a quark-gluon plasma phase to hadron gas phase and eventually reach kinetic freeze-out, where particles stop interacting with each other and fly free to the detectors. As you can see from these pictures, there's multiple stage as the system, colliding system going through, which is really complex, and also this requires want to develop a multi-stage hybrid model to describe individual phase in its own the major physics in its own phases, and then also connect with each other, connect together to describe the whole evolution of the systems. So what we want to learn about quark-gluon plasma in these heavy ion collisions, especially from the highest energy at the LHC down to RHIC, and also to lower energy at the future FINITE and NICA, is trying to understand how QGP behaves in thermodynamics and also transport properties. For example, we'd like to understand the equation of state of the quark-gluon plasma, how energy density pressure changes in terms of temperature and chemical potential, also the speed of sound. One of the major experiments goal in these heavy ion collisions programs is to try to identify whether there's a critical point and its location of the critical point in the phase diagram, and its associated first order phase transitions. The observables that are currently now sensitive to those equation of state are actually listed on the right-hand side. More importantly, the heavy ion collision is a rapid dynamical evolving systems. We would like to understand the initial state fluctuation spectrums, as well as baryon stoppings as we go to lower energies. The transport dynamics, for example, the transport properties such as shear and bulk viscosity of the quark-gluon plasma, and last but not least, the charge diffusions, and also how QGP can shine electromagnetic photon and leptons. So I list a partial list of the experimental observables that are sensitive to those properties that experimentalists use, and we want to develop a dynamical model to basically link the physics of the underlying physics in the property of the quark-gluon plasma to the experimental data, and then build up the connection to actually extract those information from the experimental measurements. So the major tool we use is to study the collectivity of the heavy ion collisions using hydrodynamics. So as hydrodynamics can be understood as a long wave effective description of a strongly interacting system, it's based on conservation law of energy momentum and also conserved charges, plus equation of state describing the properties of the underlying matters. So it can be actually applied to a variety of the interacting system. For example, at the large scales, you can actually describe the evolution of star formation in astrophysics. And also you can model using hydrodynamics or fluid dynamics in general to model the air dynamics of going through a race car in our daily life. And we also, in our field, we apply hydrodynamics to describe the dynamical evolution of the quark-gluon plasma in the strongly interacting phase. And it's worth also pointing out that our field is also very rapid evolving, trying to understand the theoretical foundation of relativist heavy ion collisions, and actually has done a lot of leading work on the theory development in the recent few years. So let me just show you examples of applying hydrodynamics as an effective and also a robust framework to describe the quantitative evolution of heavy ion collisions, where in this study, we start from the largest heavy ion collisions that is conducted in experiments like uranium collision, RHIC, down to the smallest collisions like proton-protons. And here, as I highlight, just data to model comparisons for the elliptic flow coefficients at both at RHIC and LHC energies for different types of systems, from uranium, gold to isobarons, and also small systems at RHIC. At the same time, we use the same model parameters, which I want to emphasize that all these calculations are done with a single set of model parameters, that is tuned first to the RHIC measurements, then extrapolate to LHC. As you can see that the model is doing a decent job to describe the flow measurements in lead-lead to xenon-xenon and to smaller P-lead collisions. We have a discrepancy for the PP collision 13 TeV at the current framework, which need to require some additional effort to understand the discrepancy. But overall, you can see that the hydrodynamic model with the initial conditions as well as hadronic transport can actually do a very good quantitative descriptions over of the measurements over several order magnitude in terms of charged hadron multiplicities. So this is actually done in the high energy top RHIC and RC energies. And now we want to extend this successful framework down to lower energies at the RHIC. Before I do that, there's also progressing a collective effort in the community to actually impose phenomenological constraint on the transport properties of the quark-gluon plasma at mostly at top RHIC and RC energy, where the phenomenological studies are most extensive study. So here is a yearly progress constraint on the transport properties of the quark-gluon plasma, namely the shear viscosity and specific bulk viscosities as a function of year. So starting from around year 2012, so we have the IP plasma initial conditions initially develop, and then these actually can first achieve a quantitative descriptions of all the VN data as well as their distributions at the RHIC and RC energies. And the constraint on the shear viscosity is around 0.1 to 0.2, depending on the collision energies. As we progress to 2015, so we can see that that we first introduce non-zero bulk viscosity in the hydrodynamic descriptions, and you can see that with this large bulk viscosity, which is necessary to fit the mean PT measurement experiments, we need to reduce the value of shear viscosity by almost 50% compared to the previous study. In the same year, there's also a mini-jet saturation model, EKRT model proposed, which is similar to the saturation physics compared to IP plasma. As you can see, without bulk viscosity, you also need a large viscosity around 0.2 to fit to the RHIC and LC data. As we progress to 2013 or 2017 and 18, where the lattice QCD actually had a major progress, that the equation of state actually from the two big collaboration actually converge with each other, and they actually now being incorporated in the hydrodynamic simulations. With the updated lattice QCD equation of state, there's a first this is the first Bayesian analysis carried out by the Duke Ohio State group using the LHC data, which is constrained by this orange band, which is a different approach compared to the previous approach, where the data to model comparisons basically using eyeball judgment. But here, a more systematic statistical tool is used to actually use Bayesian techniques to constrain the model to data comparison and actually extract out the temperature dependent shear and bulk viscosities. The latest effort in this end is actually done led by the JetScape collaborations, where you combine both RHIC and LC energy flow measurements and actually use a more systematic and more less unbiased prior in this Bayesian analysis. As you can see that this actually calculation actually allow a larger bulk viscosity compared to the previous calculations, and actually it's actually agree now quite reasonably with the eyeball calculations using based on IP plasma calculation. Actually, if you can see that using different types of initial conditions right now actually agree quite well with each other within the uncertainty band. So this actually is a really good progress on trying to understand or characterize the property of the QGP in our field in terms of shear and bulk viscosities. As we're stepping ahead to lower energies, we would like to understand heavy ion collisions in these phase diagrams. Mostly we want to understand the properties of the heavy ion collisions at the finite chemical potentials. So this is the heart of these RHIC Beam Energy Scan programs, and also future NICA, FAIR, and also JPAC heavy ion programs. And also I indicate that there's a link to the latest neutron star mergers physics, which actually lives in the large chemical potential and the very low temperature corner here. So if we extend the heavy ion studies to even further, we can get some useful communication with the other nuclear astrophysics communities. So the program in the Beam Energy Scan program is really really exciting, because we actually want to search for the sign of a critical point, which is a landmark in these QCD phase diagrams. In terms of dynamics, we can actually constrain trying to learn about the transport properties, not in terms of just temperature, but also its dependence on chemical potentials in terms of baryons and also strangeness and electric charge. Last but not least, we can also access new transport phenomena, especially charge transportations or diffusions of conserved charges when you go to these low energies where this net baryon charge is not zero. So in order to build up the dynamical simulations, first we need to actually extend the equation state of QCD matter to finite densities. This has been actually approached by several groups nowadays, and then mostly we rely on a Taylor expansion using the lattice QCD calculated susceptibilities here in this formula, and extend the pressure from μB equals 0 to finite chemical potentials in terms of μV, mu charge, and mu strangeness. And then we need to match this to a hadronic resonance gas models, where you can map the lattice QCD data to a hadron gas where in the hadronic phase. So here I just show you one work that we have done to build up such kind of equation state, which is building a strange neutrality conditions and also required electric charge density to be 0.4 times of the baryon density, which is the approximately average conditions for heavy ion collisions to happen for gold-gold and lead-lead collisions. Here I show you a 2D contour plot for the pressure over T to the fourth as a function of temperature and chemical potential. And the line here indicates some entropy per baryon, constant entropy per baryon density curve along this in this equation state. So in the middle plot, I show you the speed of sound, the square of speed of sound for these energies. As you can see that the speed of sound and function temperature at different collision energy along these trajectories are not so much different from each other as you go to the large chemical potentials. There's only a few percentage change as you go down to say 14.5 GeV. It's only the speed of sound is slightly higher than the one at μB equals 0, around 200 GeV. So what this means is that the acceleration rate for the flow velocity due to the pressure gradient will be expected to be more or less similar or slightly faster at the finite chemical potential case compared to 200 GeV. But on the right-hand side, let me now emphasize the effects of imposing this strange neutrality in this equation state. Here we look at the ratio of different particle yields. So you can think this is basically hadron chemistry for the measurements at the lead-lead collision at the top SPS energies. So here we choose a switching energy density from hydrodynamic phase to URQM hadronic transport to be a constant energy density surface. As you can see that if we only have baryon currents, but doesn't impose strange neutralities, we kind of doing okay job for pi plus versus pi minus, but we miss kaons, the ratio between k plus, k minus, as well as the ratio for the multi-stage hadron. So for example, the ratio between anti-lambda or anti-omega over omega is largely or underestimated compared to the measurements. Now, if we actually impose strange neutralities, that you can see that from the blue to the red points, this is actually the effect of strange neutrality improvements on the hadron chemistry. You can see that with the red points, we can now actually achieve a reasonable job description of the multi-strand hadron yield with imposing this hadron, imposing these strand neutrality conditions. It's also seen in the kaon that you can see that the difference between k plus and k minus is largely actually explained by the imposing of the strand neutrality condition in the equation of state. Another point that I want to make is that with this build up, only with this construction of the equation of state at the finite chemical potential, that enabled the hydrodynamic or dynamical description of heavy ion collision at these lower energies. Now we go to the lower energies. We really need to think about the dynamics in three dimensions. So this requires us to actually go beyond the regular, the usual assumption that for the BJORKEN Bose invariant assumptions that we make in higher energies. And these actually really lead to a series of work in the community trying to develop more realistic 3D initial conditions for these heavy ion collision at the lower energies. So also here I basically list a few different approaches that people took in the literatures that actually trying to do these generalizations. So let me start with the most simplest generalization based on geometry that I have done with my students recently. So here we want to actually trying to build the initial conditions based on the Glauber geometry and use as less parameter as possible and to generalize the initial condition to 3 dimensions. So what we want to use is trying to impose the longitudinal energy and also longitudinal momentum conservations in this model to actually eliminate a few parameters that we can in the 3D parameterizations. So the main assumption here is assume that whenever the nuclear thickness function T and TB coming from the 2 nucleus, they deposit all the energies and the momentum into the fluid. So in this case, we can calculate from the initial state the initial energy and the net momentums based on the TA TB of the incoming nuclear thickness function between the projectile and target. So if the projectile and target are asymmetric, you will have a net longitudinal momentums actually can be calculated by this formula. You can transform this energy and longitudinal momentum into 2 variables that is convenient to use, which is the center mass rapidities as well as the invariant mass. And you can notice that the invariant mass actually is more or less proportional to square root of TA times TB when this coach factor of Y being is large. So further, we actually don't want to introduce any parameters. We still assume the velocity profile in the longitudinal direction to be the BJORKEN flow. And the energy density profile is a flux tube along the longitudinal directions. Through these assumptions, you can directly see that the normalization of the energy density profile, which is usually a constant of parameters in the model, is now actually can be directly linked to these invariant mass parameters, and actually is constrained by the total energy conservations. So it's not a free parameter anymore. So for 5 GeV above, where this coach factor is much larger than 1, we found that the energy density in the transverse directions in this model is naturally proportional to square root of TA times TB scaling. And this is actually a scaling that coming out from a global fit using Bayesian analysis to the RHIC data. So from this model, actually, if you assume these assumptions, these square root TA and TB actually come out naturally from the model. So here is a contour plot of how this initial condition looks like in 3 dimensions. So on the left top plot, I just show you the energy density distributions in terms of transverse direction X and also longitudinal direction eta-S. So since we assume the energy density is a flux tube, here the density contour is color coded here. So you can see that it's basically a cylinder in the longitudinal directions. But as you can see, if we go to the edge of these fireballs where the thickness function becomes asymmetric between projectile and target, you can see that the flux tube actually shifts to the right. The center of the flux tube is actually in the positive eta-S correlate with the spectator directions indicated in this blue blob here. So this is actually the effect of the imposing the net longitudinal momentum conservations, which shifts this profile to the forward directions. And the lower panel show you the transverse snapshot of the energy density profile in the transverse plane. So for example, at the middle is basically the middle rapidity profile here. If we take an event average profile, it's like Helmholtz shape, as we already know. But if we go to forward and backward direction, the fireball become more eccentric and also develop a dipolar deformations in the forward and backward directions. And this can be qualitatively reflect in terms of the eccentricity, initial eccentricity for the epsilon-1 dipole deformations and elliptic deformation is a function of eta-s. So for example, for elliptic deformations, we have some elliptic non-zero value in the middle rapidity, but as we go to forward rapidities, the fireball become more eccentric, and then we get large eccentricity from this model. So with this model, we can just now tune to calibrate this model and then actually test whether this model has any predictive power. So here we use using the existing data from Phobos to calibrate our model. So in our model, the only model parameters in 3D is the width of this plateau. The height is actually constrained by the energy conservation. So we just need to tune the width of the plateau for different collision energies to match the data. And then once we match the central collisions, all the other peripheral collisions are actually model predictions from these calculations. As you can see that the central dependence of these particle productions as a function of rapidity is reasonably produced at the RHIC energy from 200 GeV down to 19.6. And we also do a similar exercise at the SPS energies for the two SPS energies that measured in the literature. Again, we first calibrate our model in the most central collisions, and then you can see the prediction from this model in the semi-peripheral collisions. And overall, you can see that the model doing a decent job once we impose this energy and momentum conservation. So we can also do another conditions at the Beam Energy Scan program that the STAR is currently measuring. So at this stage, STAR only have measurements at the central rapidities, y equals 0 for the particle yields. But actually, our model is only have one free parameters in the two directions. We can basically use this central point to fit to the data, and then the rapidity distributions here actually is our model prediction, and it can be further checked to the experimental measurements. And also you can see that the prediction for the central dependence is not accurate if you go down to 40 to 50%, but more or less reasonable describe the experimental measurements here. So one serious test of this model is actually going to the asymmetric system, like small system like D-Gold, where the projectile and the target are highly asymmetric. So on the left-hand side, actually, I show you that if you don't impose the momentum conservation along the longitudinal directions, you actually will largely overestimate the production of particles at the middle rapidity compared to the one actually you impose this. And believe it or not, these two calculations actually is tuned to the same collision energy, the total energies. But you can see that the particle production in the middle rapidity is about factor of 2 compared to the other ones. It's mostly because that the rapidity distributions in the forward directions are slightly different, and the energy of if you constrain the total energy, you need to times coach eta to the particle spectrum to actually the rapidity distribution to actually calculate the energy. So the two curves actually carry the same number of collision energy in total, but the small change in the rapidity shape in the forward direction actually leads to a bigger change of the particle production in the middle rapidities. So the distributions at the forward rapidity are actually quite important for us to constrain the model. Using the model, we can now calculate the D-Gold particle distributions for 200 down to 19.6 GeV, where there's a FINITE measurement for this Beam Energy Scan for these small systems. As you can see, this model reasonably reproduced the central mass of these rapidity distributions. However, the slope is too flat compared to the measurements, which I will come back later once we have more improvements on the model side. From this study, we can also study the other observables, like elliptic flow at the RHIC measurements. From here, what I want to emphasize is that we can actually introduce a temperature and chemical potential dependence on the shear viscosity to actually study the flow measurements at the Beam Energy Scan at functional collision energy. And this is first carried out by these people in 2015, where they actually extract on average shear viscosity per collision energies. But more physically, you can actually parameterize the AWS as a function of TMUB, and then tune it such that you can actually describe the measurements at different collision energies. Here I can show you two plots on this study, on this exercise. One is that if we look at a fixed energy, but the V2 as a function of rapidities, as measured by the star in these black solid points, we can see that if we have just a constant shear viscosity calculation in the hydro simulations, you will get this green line here. And you can see that there are somehow kind of this bending up of this V2, which is reflect the initial shape of epsilon 2, as I indicated in several few slides ago. And you can see that if we turn on the temperature dependence, for example, we have this lower rising tail in this lower temperature, then we go from this green to the red curve here. So it actually suppresses the V2 at the high rapidity, where most of fireballs stand at the lower temperature, so that you get a larger effective temperature. But the largest suppression you can see from the red to the black is coming from the chemical potential dependence, where basically you can actually, at 14.5 GeV, you actually have a large shear viscosity in the finite chemical potential compared to the 200 GeV. So that with all these dependence included, you can get this black curve, which is close to the measurements. So in terms of matching the shape of this rapidity dependence of V2 actually give us some handle or constraint on the TMUB dependence on MUB, on the shear viscosities. So similar story can be studied, the V2 as a function of collision energies. As you can see, we again present the V2 measurement, but now it's at the central rapidities as a function of collision energies. As you can see that if we order to match from 200 GeV down to 7.7 GeV, you actually need both temperature and the chemical potential dependence on AWS to get this correct slope of this V2 as a function of root S. So we can also do some.
Chen, before you move on, maybe you can stick on that previous slide and tell us if there is some functional form for eta over S as a function of mu B, and if there is theoretical guidance in your parameterization that you're showing here.
Right now, there's no theoretical guidance, so I just took some simple function with one parameter, trying to fit to the data. But if there could be some, we can take some guidance from perturbative calculations in this from these directions. Maybe that will give us better parameterizations. But right now, this is just a guess, a simple guess of the functional form, and this is what you get.
Thank you. Just move ahead.
Yeah. Okay. Now we also look at is, say, for example, HBT radii from these calculations. So here I show you the calculation for R out, R side, and R long as a function of root S from these simulations. What we found is that in these particular initial conditions, the R out is actually, so the R long is actually overestimate, and needs some further investigations how to actually improve the model. But R side and R out actually are quite reasonable to reproduce with compared to the star measurements. And also with the current calculation, if we do the exercise by just calculating the square root of R square minus R side square, our calculation is basically flat as a function of root S, where the data somehow shows some kind of non-monotonic behavior on the scale, but the scale is not that large. So this also needs some further investigation whether this non-monotonic behavior is indeed going to be originate from the softening of equation state at these relative energies. So we can actually now start to actually build in theoretical studies towards this trying to understand this non-monotonic behavior. So so far I tell you just the simplest extension to 3D. So we were, as a theory, from theory, we actually want to do better to be more microscopic. So here I just highlight one example that we want to describe some microscopic physics during these collisions. So this is 3D Glauber plus string model where we actually introduce event by event fluctuations, as well as trying to model the energy loss of these incoming nucleons or incoming pair of quarks. Here, so if I draw this diagram, so if we consider two either nucleon or valence quark to collide with each other, and we assume they produce a string contain energies from the energy loss from the two incoming colliders, we can actually parameterize this energy density inside the strings to be the energy loss from these two quarks. And also we can actually put the baryon densities at the edge of the string most of the time, and also include the remaining energy for these quarks in there, as the Gaussians at the edge of the string. And also phenomenologically, the baryon density has to be at the end of the string. They can actually fluctuate to the string junctions, according to a paper by Dima in around 1996. So we also implement this in the model, trying to see whether this is necessary or whether this has phenomenological impact in the model simulations. Of course, as we learn from the same polar models, the imposing energy and the longitudinal momentum conservation is actually extremely important, and this model also impose this in their building. So with the string model, you can actually look at the space-time distribution of these strings as a function of rapidities. And you can see that at 200 GeV, the two nuclei are actually highly Lorentz contracted. So all the strings are distributed almost in a like cone in these TZ coordinates. If I translate into tau eta coordinates, which is a coordinate is usually used for the hydrodynamic simulations, if you look at a single like cone, tau will be a constant here. And you can see that this is indeed true at the middle rapidities. However, at the full rapidity, there is some spread of the string source as a function of tau. And this can be understood as the right picture here. So if you boost your nucleus to a large rapidity, or you just go along with one of the nucleus in the full rapidities, the extensions in the longitudinal direction for that nucleus is actually less Lorentz contracted, so that you can think about this picture as a thin sheet of another target going swipe through your big nucleus, so that give you this finite spread of the strings at the forward directions. As we go down to lower energies like 220 GeV, so then even in the middle rapidity, the Lorentz contraction is not small, is not large, so that you also get finite spread also in the middle rapidities. So with this finite extension of the interaction zones, you actually need to develop a scheme which we call dynamical initialization scheme to actually initialize hydro where the source turn appear at different time and the positions. So here I just have a cartoon indicate that if you consider this finite thickness of the two incoming nuclei, you have a finite interaction zone here, and then these will actually generate a source turn deposition regions for the hydrodynamics to evolve. And this has been written at the source turns on the right-hand side of these hydrodynamic equations. And this scheme has been adopted by a few groups in the world to actually take these into account. So as examples, I just show you a series of cartoons, how this is set up in terms of simulations. For example, at 20 GeV, so we have two nuclei collide with each other. So we first freely propagate these two nuclei to touch with each other. And then this is when we actually start our hydrodynamic simulations. So you can see that at 0.5 Fermis, this is the first energy depositions in one of these collisions. And now I just want to plot this energy density contour in 3D in these T, X, Y, Z coordinates. So as you can see, when the two nuclei are starting to cross each other, you have more and more energy density actually deposit into the medium, indicated this contour in these 3D dimensions. As you can see that after about 2.5 Fermi, the two nuclei are actually fully going through each other, and you will have basically a three-dimensional energy density blob in the hydrodynamics for the hydrodynamics to evolve. And you can basically just evolve to late time. Yeah.
So maybe just to this picture, can you define your time equals 0? Somebody is asking, what is your T equals 0?
Oh, the time equals 0. The time equals 0 is, sorry, the time equals 0 is basically when these two nuclei just touch each other. So the two nuclei, the first two nuclei just touch each other. That's where I define time equals 0.
Thank you.
And then you have some Sawston deposit, and then this first Sawston appears in the hydro by 0.5 Fermi. Yeah, so this is how this hydrodynamic simulation looks like in 3D. And then we can actually now study observables. So first we kind of want to have a side-by-side comparisons whether this extra thing we include in event by event fluctuations with dynamical initial scheme actually worth the effort compared to the cheaper or simpler event average simulations. As you can see that for the heavy ion collisions, in GO-GO collisions from 200 to 19, the repeat distributions are more or less similar to the one that was event average. However, if you go to the DGO collisions where I initially discussed that the event average profile actually failed to develop the shape, to describe the shape, the event by event calculations actually describe the shape much better compared to the event average simulations. So this indicates that in these asymmetric collisions that we actually can see some event by event fluctuation effects even from these DN data measurements. And we can go one step further for these event by event simulations to look at, say, system size dependence for proton gold, D gold, and helium-3 gold as a function of rapidities, and also their V2 measurements that can be compared with Phoenix. So this is actually, so you guys can see that this is just a purely model extrapolations. Once we fix the GO-GO collisions, there's no free parameters. They are all just model predictions from this model. This is actually, the agreement with data are not good, also not bad. So this is just, we have some qualitative agreement with the data, and this I think is a good starting point to actually start to understand the longitudinal fluctuations. And these asymmetric systems from D gold to helium gold, even copper gold, then to gold gold is actually a very good series of systems for us to study the longitudinal fluctuations in the RHIC. And also there's also more detailed measurements on these V2 correlation, decorrelation measurements at both RHIC and FC energies for different energies. Here, so if you have a longitudinal fluctuation of the two fireball, the orientation of the density distributions will be different at forward and backward directions, which leads to decorrelation of these measurements. And there's a nice paper by Sumi Saka and Kastu that's showing that both thermal fluctuations as well as the initial longitudinal fluctuations are actually important for these measurements, which requires more substantial improvement on the theoretical calculation to include these thermal fluctuations in addition to the initial longitudinal directions to study these observables. And here's a recent measurement of these V2, of these R2 variables as a function of rapidities for two different energies at 27 and 200 GeV. If you scale the measurement, the R2 by the Y beam, you can see the experiments data actually scale nicely with each other. But the theory actually give you some deviation from each other, these two energies, which indicate that the theory, the longitudinal fluctuation theory may be too large. And also this actually give us some constraint trying to determine the parameters in the longitudinal direction for these models. Now I want to also come back to the questions whether it is needed for this early time dynamics to understand whether the difference between these dynamical source turn depositions and or you just do a one shot of simulations with everything depositing a fixed proper time, whether you can see any phenomenological impact on that. So as you found in the hydrodynamic simulations, you do see the difference. For example, in the dynamical simulations, you see the temperature gradually build up from 0 as you deposit more and more source turns, and then actually the fireball lives about 2 Fermi longer compared to these instantaneous depositions, because if you have everything deposited initially, you have a stronger gradient, so the system actually could expand faster, so the system lives shorter in these collisions. On the right-hand side, I show you the development of the moment anisotropy, which can be related to V2. As you can see, that instantaneous depositions actually develop V2 higher than the dynamical one, because if you have source turn gradually depositing into the hydrodynamics, you will just have more more interference between different hotspots and also destroy a lot of V2 during the evolutions. So this means that, all these simulations will translate to a small difference in the measurements. For example, in the PT spectra of pions or the V2 of pions, you can see the difference between the two simulations are quite small. So with the dynamical initialization, about 5 to 10% smaller radial flow and also elliptic flow as you would expect from the hydrodynamic simulations. So in hadronic observables, maybe it's not very sensitive to this setup of the dynamical simulations. However, if you look at other observable like the electromagnetic probe, which is an important observable at the RHIC Beam Energy Scan program, you can actually see that there's a depletion of the space-time volume or the early time. Compare this dotted line with this instantaneous versus this dynamical setup. So this will actually restrict a lot of thermal radiations in these dynamical evolutions compared to these instantaneous. So this result a suppression of the photon in the high PT. More importantly, you can see that the signal for V2 in the direct photon is actually much sensitive to this early stage dynamics. So this means that the photon electromagnetic probe, like photon dileptons, actually sensitive to the early stage of heavy ion collision at lower energy, and it can actually provide us independent handle on how to constrain them in these model calculations. So with this setup, we actually did a thorough study of the radiation of the thermal radiations of photons from 200 GeV down to 20 GeV. As you can see that compared to the prompt source from the initial collisions, the thermal radiations has a sizable contributions even down to 19.6 GeV. And also in the lower panel, you can see that the direct photon actually contain significant V2 as even you go down to 19.6 GeV. And I point out that even if you look at 20 GeV, the jet production is more strongly suppressed because of the root S, and the photon dilepton actually serve as a unique probe to this as a tomograph probe for these heavy ion collision at these low energies. So last but not least, let me just illustrate that in the lower energies, we can also trying to study new transport phenomena of quark-gluon plasma in terms of charge diffusion. So for example, if we evolve the equation of motion of hydrodynamics, which involve energy momentum conservation and charge conservations, in the charge conservation, you can actually include a dissipative currents, which is the charge diffusion currents. So the physics of charge diffusion currents is basically tell you how the charge can diffuse out or into the fluid cells as the fluid cell is moving. So it has a transport property associated, transport coefficients associated with these currents, which is kappa, which is the charge diffusion coefficients. If you have multiple charge, then you will have a matrix, which also tells you that there's a mixture between different flavor of charge that can be diffused from each other. So this is more or less illustrating this cartoon, this picture, such that you can think about conserved charge as these different colors of ink inside this quark-gluon plasma, and you can see how they. You want to study how they diffuse in this glass of water. In the heavy ion collisions, the QGP actually is fastly expanding, so you actually can look at these the effects of charge diffusions in terms of net proton distributions, in terms of rapidities. And you can see that because these diffusion are driven by the gradients of chemical potential over temperatures, you can see the gradients of the density gradients actually is actually pointing inward. So actually, if you include a large diffusion constant, you will have more baryon transport into the middle rapidity. And this is more clearly shown in the 19.6 GeV, so that you can see that with and without diffusions, you will get the shape changes in these net proton distributions. And recently, there's a work trying to include all three types of conserved charges: the baryon charge, electric, and strangeness. And what they show is that these diffusion processes are not orthogonal to each other. They actually can mix with each other. So what they show here is basically the density distributions as a function of rapidities, evolutions for several scenarios. So the first is without diffusion, as you can see from the black to the red points to the red dotted lines, the shape of the baryon density doesn't change much. So if you turn on only the baryon diffusions, you can see that more and more baryon actually transport into the middle rapidity because of the gradient is pointing inward. And you can include, say, off-diagonal line in this matrix where mix the baryon charge and all these charges. In this case, is the baryon and strangeness. And you can see that the baryon density doesn't change much, but you actually develop a non-zero strange density, a strangeness density, because of this cross-feeding between the baryon density and the strangeness. And last but not least, if you include the full diffusion matrix, you can see that the shape of this net strangeness also change from the non-off diagonal to the diagonal ones. So you can see that for those calculations, if you want to understand about the strangeness current, for example, simulation with involved with lambdas, then you actually need to have these descriptions included in the calculations. But however, if you look at, say, at the 200 GeV, so if you think, okay, so if my initial baryon density is basically just this dashed line, if I just want to turn on the diffusions, and hopefully that the diffusion can actually diffuse more particle into the middle rapidity, actually this is pretty hard in the simulations. You will find that whatever you take the large diffusion constant, the diffusion from the hydrodynamic phase is only about 0.5 to 1 unit in terms of rapidities. It's very hard to actually transport a baryon charge from like rapidity like 3.5 to the middle rapidity equals 0 from the hydrodynamic and the sequential hadronic transport simulations. So any large baryon stopping as needs to be happen in the early stage. So here, what we use is trying to actually include this string junction fluctuation for the baryon density in this string model. So if we actually turn off the string junction, assign all the baryons in the string end, you can get this black dash line, a black line. So the only way you can get this 200 GeV measurement at the middle rapidity, this non-zero net proton distributions, is trying to turn on the string junction in this model, so that the initially that the baryon can actually stop to much lower rapidity, so that during these evolutions you can actually get a better agreement with the measurement by early measurement Browns. And here on the right hand side, I show you that this model with this string junction model does not only work for 200 GeV, but also can consistently work down to lower energies, even to 7.7 GeV. So these early time string junction fluctuations also will play a role if you want to extract the baryon diffusion, the coefficients based on the shape of this dNdy of net protons. Another direction to actually access this baryon diffusion constant is trying to look at the the fluctuation of these charges. So according to the dissipation fluctuation theorem, so whenever you have diffusion effects for this charge, you will also need to include the event by event thermal fluctuation of producing these kinds of charge pairs. And then they will eventually imprint into these balance functions for K plus K minus or proton antiprotons. This work is proposed by these people. And you can see that if you change the diffusion constant, you will actually change the shape of this correlation function in the delta phi directions. Similar study can also carry out in delta eta for these balance functions. And you can see that for a large diffusion constant, you will have more flatter distributions of these correlation functions, indicating that you will have more diffusion for these pair evolutions during the quark-gluon plasma. And this actually is an independent observables compared to the net proton distributions to actually help us to access this charge diffusion process. But also the actual shape of this balance function is very sensitive to the underlying flow profile. So a global fit is necessary to actually help us to constrain these new charge diffusion coefficients. So here now I just come to my summary. So I hope I just give you a kind of overview that heavy ion collision has been done over 3 order of magnitudes in collision energies, and these are actually extremely valuable for us to study the phase structure of the hot QCD matters. So the goal for us is trying to see find or locate the critical point. And also this, at the large mu B, we can actually now build up connections with nuclear astrophysics communities in terms of these merger dynamics. In the RHIC programs that we have now started to develop this 3D hybrid framework, and you can see that we are starting to have a quantitative descriptions of the bulk observables. So this actually this requires the inputs from lattice QCD to give us guidance on how the equation of state changes finite mu B, and also help us to learn about interesting physics like initial baryon stopping, charge diffusions, or collectivity of quark-gluon plasma when we have a rich baryon environment. And eventually we are trying to actually aim to develop a unified and consistent descriptions for the 3D dynamics from PP to PA to AA collisions and for all these collision energies. So thank you. So that's all.
Thank you.